Hello and welcome to 6.4 Differential Equations. This video is going to be shared with the SMA staff so that we have a whole all-encompassing example all in one of one online lesson being taught with a video like this one. So this is Calculus AB. We are covering 6.4 differential equations. We're going to start by defining a differential equation, and particularly a separable differential equation. So what is a differential equation? A differential equation is any equation made up of differentials. Now we've talked about differentials before and what that is, but a differential would be like dx. You might see that in part of a derivative, you might see that in part of an integral. That's a differential, right? Whenever we talk about the integral of f of x dx, then there's the integral, the integrand, and then the differential, right? So a differential equation is an equation made up of differentials. Now it's not entirely made up of differentials, but it does contain differentials. So an example might be dy dx equals, let's just say, f of y g of x. We're going to talk about that a little bit more in just a second. So let's start by defining a separable differential equation. All right, here we have our definition of a separable differential equation. A differential equation of the form dy dx equals f of y g of x. When a differential equation is in this form, we call it separable because we can separate each side of the equation, where one side of the equation has x and the other side has y. We separate the variables using the form 1 over f of y dy equals g of x dx. We simply do that over here by dividing one side by f of y and then multiplying over here by dx. All right, now let's move into our first example. This is example number 1. It can be found on page 350. Our prompt is to solve for y if we're given dy dx equals the quantity x times y squared, and given that x equals 1 when y equals 1. So this is what would be given to you in an example you might see in your homework or on an AP question. This is from the textbook. The rest of our examples for this section are going to be AP questions from AP's website. Of course, as I described before, we're having changes to the AP exam in terms of calculator, no calculator, structure, and timing, and all that stuff. But these are still AP questions that were on AP exams in the past. What's going to happen in the future, we're not entirely sure of at the time of recording this at the very least, other than what I've already shared via Google Classroom. So for this particular example, this is the prompt. Solve for y if dy by dx equals the quantity x times y squared, and x equals 1 when y equals 1. So to find the solution, first I'm just going to write off to the side solution so that it's clear that this is the prompt and this is the solution. For this particular example, I'm going to encourage you to just follow along. Maybe listen to me say it the first time through, watch me work it out, and then rewind the video and maybe step by step write stuff down in your own notes so that you can kind of get a feel for it. On the next example, I'm going to encourage you, and all following examples, I'm going to encourage you to pause the video, try and work it out on your own, and then compare your answer to what I show on the board. And if there are differences, then you can pause and try and figure it out and go from there. That's my encouragement to you. So the solution for this particular problem, I'm going to start by rewriting this. So I have the quantity x times y squared. I can rewrite that as the quantity xy times the quantity xy. If I distribute that, I have x squared y squared. That should make this a little easier to work with. So now that I've got x squared y squared, and I know that this needs to be in the form dy by dx equals f of y times g of x. So that means dy dx equals x squared y squared. So then it's not too terribly difficult to extrapolate from that. This is the x part and this is the y part. So then f of y must be y squared and g of x must be x squared. Meaning now, since this is a separable differential equation, it is separable because I can write it in the form dy dx equals f of y g of x, just like this. So now I'm going to separate those out in the form given to you in the example so that you can try and see what y is. So that's how we're going to get to y. So I'm going to erase just a little bit here. I'm going to leave the prompt. I'm going to erase this part. And I'm going to erase all of that. So remember that form that I talked about was 1 over f of y equals g of x dx. F of y, we already said, was y squared, and g of x was g squared, or x squared. So 1 over f of y, forgot my dy, 1 over f of y dy is going to be 1 over y squared dy. That'll be equal to g of x, which is x squared dx. Okay, cool. Now I have a differential equation. I can solve this. It might be confusing to figure out how I might solve this, but if I want to solve it for y, what do I have to get rid of? The differentials, right? I have to get rid of dy and dx. I can't have dy and dx unless I want y as an equation, as a function of dy and dx, but that wouldn't really be anything that makes sense, right? That'd be kind of, we don't want that. No, thank you. So, to get rid of the differentials, how do you get rid of differentials? Well, how do you get rid of a derivative? Let's see, I think we threw a party for that. I think we threw a party for how you get rid of differentials. What was that called? Oh yeah, it was the fundamental theorem of calculus. The most important thing we've learned all year, the epitome of the beauty of calculus, remember? So, which, if you recall, the first part of the fundamental theorem of calculus says that to get rid of a derivative, you integrate it. And to get rid of an integral, you differentiate it. So here we have differentials, which are part of derivatives. So to get rid of them, I'm going to integrate both sides. So I'm going to switch whiteboard marker colors to show that I'm doing something new. So I'm going to integrate on the left and integrate on the right. And then my integrals and my derivatives are going to take care of each other, my differentials. Because, what's this say on the left? It says the integral of f of y with respect to y. On the right, it says the integral of x squared with respect to x. So if I want to move on from here to be able to solve for y, what do? I do the integral. I anti-differentiate. So the antiderivative of 1 over y squared, if you think you know what that is, now's a good time to pause, write it down, and compare to what I'm about to tell you. The antiderivative of 1 over y squared, well, we could treat 1 over y squared as y to the power of negative 2. And then whenever I anti-differentiate, remember, I add 1 to the power, and then I divide by that new power, which if you don't recall, that was x to the n plus 1 over n plus 1 is the form of how that looked. That should be in your notes if you wrote it down in class. We've done it lots of times, but I know that we just had spring break and now we're online, so things might be a little rusty. So what I'm going to do when I anti-differentiate this, when I integrate both sides over here, I'm going to add 1 to that power, and negative 2 plus 1 is negative 1. So I'll have y to the negative 1, and I'm going to divide by the new power, and dividing by negative 1 is just going to make it negative. So I'm going to have negative y to the negative 1. Now I'm going to erase that. Now my x squared, to anti-differentiate that, I'm going to do the same thing. It's just going to be x squared, add 1 to the power, divide by the new power. So that's going to be x cubed over 3. Now, I know what you're thinking, Gabe, you especially might be thinking, Mr. Alsbach, where's the plus c? Well, I'm just going to put it on the right side. I'm going to solve for y, so I might as well just put it on the side without y. Now, you might be thinking, well, shouldn't we have a plus c on both sides? And here's what I'll tell you. You could have 1 on both sides, but then the algebra is going to get weird, because if you said, like, y, some y thing plus c equals some x thing plus c, I wanted to solve that, I would subtract c from both sides, and I have c minus c, which would just cancel. But that's not necessarily the case. I could still have a constant. So we just put it over here, and then we're going to actually find what c is using our initial condition, which was given to us right here. And then we'll plug that in on just one side instead of both sides. It would be doing it twice, and that would be redundant. So let's go ahead and find out what that is. Here I have this equation, this lovely equation. So I'm going to plug in 1 for y and 1 for x, because that's what my initial condition says, and I'll solve for c. So I plug in y, I have negative 1 to the negative 1 equals 1 cubed over 3 plus c. And see, now I can solve for c. 1 to the negative 1 power, that's going to be the same as 1 over 1, which is 1, and it'll be negative, so I have negative 1. 1 cubed is 1, divided by 3 is a third. Got to keep that plus c. I'm going to subtract 1/3 from both sides to solve for c. 1 minus a third is negative 4/3, or negative 1 and a third. So that means that c is equal to negative 4/3. Alrighty, go team. So now let's come back up here. I want to right here, I'm going to take this, I'm going to plug in my plus c. So I'll have negative y to the negative 1 equals x cubed over 3 minus 4/3. Alright, now I'm going to erase a bit. Remember, you can always pause the video and rewind if you need to finish writing down. Alright, now my goal here, I'm still solving for y. I don't have y, I have negative y to the negative 1 power. So I need to get rid of those two things. First things first, I've noticed something, which you may or may not notice. Right here, I have a common denominator. So I'm going to simplify that a bit. You wouldn't necessarily have to simplify that in that way. But if you didn't, then it would just be less simplified. So let's go ahead and simplify. Since I have a common denominator, I can just do x cubed minus 4 over 3. And we're done. Ta-da! Simplified. All right, now I'm going to do two things. I need to distribute the negative to the other side, and I need to get rid of that negative 1. So let's rewrite this just a little bit. I'm going to have negative 1 over y, which is equivalent to this, equals x cubed minus 4 over 3. Now to get rid of that negative 1, it's pretty straightforward, right? We're going to multiply both sides by negative 1. We've been doing that for years. But for y, it's inverted. What I'm going to do is just flip both sides. You could also think about it as I'm going to multiply y over here and then divide this whole thing. But then I would have 1 over this whole thing, so I have to flip it. It's easier for me to think of it as 1 over y. If I want just y, then I have to flip it, so then I'm going to flip this side too. So to flip that side, I'm going to have 3 over x cubed minus 4. And then for that negative, I'm just going to multiply both sides by negative 1, just like that. And there we go. That's the solution. I have solved for y in this differential equation, given this initial condition. So let's erase everything else and leave just the solution there. Y equals negative 3 to the... I'm going to alls box my answer. Which my dad did get a kick out of that, by the way. I did tell him you guys said that, and he thought it was hilarious. So I have successfully alls boxed my answer here. I'm done. But I can always double check it if I want to. If you're in the heat of the AP exam and you want to double check your answer without using your calculator, you can simply differentiate this whole thing. If I differentiate y, then I should get my original result, right? The derivative of y